Hello, let's continue with the next section, 4.5, optimization problems. So optimization problems are kind of where we can put finding a maximum and a minimum into a type of real life situation. We're trying to find what is the most I can get out of something, for instance. Some definitions we will use are constraint. A constraint means as to what type of answer are we looking for? If you're looking for something that's like a measurement or a distance, you don't want something that's negative, for example. Or maybe you're looking for whole numbers, not decimals. So think of what type of answer you're looking for. You'll also have to work with an objective function. An objective function is another type of function that you can apply to your own function that's being applied to your question that you're working with. All right, let's see an example. A rancher has 400 feet of fence for constructing a rectangular corral. One side of the corral will be formed by a barn and requires no fence. The 3 exterior fences and 2 interior fences partition the corral into 3 rectangular regions as seen in the picture. What are the regions of the corral that maximize the enclosed area? What is the area of the corral? All right. Well, we have a picture that kind of helps us out. So we see that we're going to have fence that are the same measurements. So we're going to make up 4 fences. That is your x. And then we have a length that is your y. So if I'm just thinking of the fence I'm going to use up, that will be made up by your perimeter. So your perimeter will be adding up all the sides, right? Will be the sum of your sides. So a good equation for our perimeter would be there's 4 x's, so 4x plus the length of our y. Now this perimeter, we have a total of 400 feet of fence to work with. So whatever that sum is, it for sure needs to be at most 400. So this is a good starting point. Now, we have to think of what type of function can I relate this to? Well, it's also asking for the area. So our objective function would be that length times height equals your area. Well, we can set them equal to each other if we solve them for their meeting point or solve for the same variable. So we have our 4x plus y equals 400. Let's go ahead and solve for y, or you can do x, but y seems to be the easier one since x has a coefficient. We subtract 4x on both sides. So we're left with y equals 400 minus 4x. And we can go ahead and use that in our area formula. So y is going to replace with 400 minus 4x. So that we have x times 400 minus 4x equals our now function for our area. Notice this is really helpful because now I'm able to work with just one variable. Everything's in terms of x. All right, well, let's go ahead and find the maximum amount for this value of x. So then we find the max of x. So let's work this out. Let's multiply in that x so that I have 400 x minus 4x squared equals ax. Let's go ahead and find our derivative. Now, why would we find our derivative? Our derivative will help us find a high point or low point within our function. So what we're trying to get to, our max. All right, our derivative Luckily enough, this is just power rule. Our derivative is 400 minus 8x. Let's go ahead and set that equal to 0 and solve. Put our derivative equal to 0 and solve for x. So that we have 0 is equal to 400 minus 8x, and we're left with x is equal to 15. So that lets us know that our optimal amount for our x value is a length of 15. So now if we go back to our original function, which was 4x plus y equals 400, we see that an optimum value for x is 50. So that we have 4 times 50 plus y equals 400, and we're left with y being equal to 200. So we have found all the lengths needed. We have an x of 50 and a y of 200. You have optimized the length and height for your corral that's right along your barn. And from there you can answer the last part. What is the area? Just length times height. Alright, let's move on to a different example. Suppose an airline policy states that all baggage must be box-shaped with a sum of length, width, and height not exceeding 64 inches. What are the dimensions and volume of the square base box with the greatest volume under these conditions? So we provide a picture for you, but notice for your volume, we like length times width times height. We have two variables repeating, and we do this so that we can have everything in terms of two variables and then work with only one. Otherwise, it might be a bit too tricky with too many variables rolling around. So we'll make one of them the same. So we have W times W equals your height. Now, important piece that your question or your example reads is that the sum, so if we add them up, if we add up all three sides, they should not be more than 64. So based on that, and in our picture, we must have that W plus H equals 64, so that we have 2W plus H equals 64. And because we're working on a box-shaped region, a good objective function would be your volume. And our volume would be length times width times height. That's your volume definition. But so that we can better apply it to our function, since we have width twice, would be width times height, which would just be W squared times H. All right, so we have our two functions that we're going to work with. Now we just have to set them equal or substitute them to one another. So we can go ahead and solve for H in our first one, because that would be the easiest one to solve with, right? Without having to include too many fractions. Sometimes you can avoid fractions, but if possible, it's nice to do. So I have 2W plus H equals 64. We solve for H, so we subtract 2W to both sides. So we have 64 minus 2W, and then we work that along with our volume. So instead of H, I'm going to write 64 minus 2W, and we have V of X, or V of W, since we're in terms of W, equals W squared times 64 minus 2W. All right, let's go ahead and multiply that in so that I have 64W squared minus 2W cubed, and that is our function. Now, since this is an optimization type of problem, let's go ahead and find that first derivative and set it equal to 0. And then we're going to solve. All right, so if we find our derivative, that gives us 64 times 2 is 128. 128w minus 2 times 3 is 6. And 3 minus 1 is 2. Let's set that equal to 0. So we have 0 is equal to 128w minus 6w squared. We can factor out a w and a 2. So that we have 64 minus 3w. And we set each one equal to 0. We get w is equal to 0. And w is equal to 64 over 3. Now here's where thinking of what type of constraint you want. Well, we cannot have a width that's 0, right? Because then that wouldn't create a box, that would just create a plane or a sheet of paper if you like to think of it that way. So the one that we would want to work would be this width. All right, so we found our width. Now let's find our height by using our formula. 2w plus our height equals 64. We found a width of 64 over 3. So I have 2 times 64 over 3 plus our height equals 64. Let's go ahead and multiply that out. So 64 times 2 divided by 3. That gives us 128 over 3 plus h equals 64. Let's get h by itself. So that's 64 minus 128 over 3, and we get 64 over 3. So that is our width and our height. All right, so here are some guidelines to help you work with these optimization problems. Read the problem carefully, identify the variables, and organize the given information with the picture, the given information in the picture. Identify the objective function, the function to be optimized. Write in terms of the variables of the problem. 3, identify the constraints. Write them in terms of the variables of the problem. 4, use the constraints to eliminate all but one independent variable of the objective problems. 5, with the objective function expressed in terms of a single variable, find the interval of interest for that variable. And lastly, use methods of calculus to find the absolute maximum or minimum given the objective function of the interval of interest. If necessary, check the endpoints. All right, so our last example. An 8-foot tall fence runs parallel along the side of a house 3 feet away. So we see here for our picture, that's your fence. And we see that there's a distance of 3 feet. What is the length of the shortest ladder that clears the fence and reaches the house? So we're trying to find a ladder so that it goes through your fence and then reaches the top of your house. Assume the vertical wall of the house and the horizontal ground have an infinite extent. All right, so it's saying it's not giving you a limit for how far away your ladder can be, for example. So if we put that in more of a general picture, we have your house height to reach. We have your fence that it must clear. And we see that within that there is a starting and an end point and that 3 feet of fence in between. Thus, it's creating two similar triangles. All right, when you think right triangle, there should be a formula that always comes to mind, right? So we should be thinking Pythagorean theorem. So our Pythagorean theorem That is a squared plus b squared equals c squared. All right, but what do we want? There's two triangles that we're talking about. We want to find that larger triangle because we're trying to find how far this enclosed area, well, that outer triangle must be. Now, in terms of what we have, that would be a leg of b, so I have b squared plus that other leg of 3 plus x. So I have 3 plus x squared, and hopefully that gives us our ladder. So our ladder length squared, which would be your hypotenuse. All right, is there another formula that I can tie in? Well, this one isn't so obvious, but we have two triangles. So because we have two triangles, I can create some type of similar triangle ratio. And for this ratio, I want to work with the larger triangle and the smaller triangle, the two triangles that we have. So when I first set this up, I set this up incorrectly. So let's think of our larger triangle and our smaller. So larger equals your smaller. So your larger triangle is made up of b and 3 plus x. So that we have b over 3 plus x is equal to our smaller triangle. What is our smaller triangle? Our smaller triangle is 8 over x. 8 over x. Now, if I can solve for a variable, then I can go ahead and work it in with our Pythagorean theorem. A good variable to work with would be b. So let's go ahead and cross multiply and solve for b. So let me tell you about my mistake when I was working this out earlier. For some reason, I ignored the fact that I need to work with two triangles. So I just was very careless with picking my sides. That's why I took the moment to highlight the sides corresponding to your larger and your smaller triangle. All right, so we have, let's cross multiply. We have b times x, which gives me bx equals 8 times 3 plus x. All right, we want to get b by itself, so let's divide by x, so that we have b is equal to 8 times 3 plus x over x. All right, so our new formula, we're going to replace our b with our new value for b, so that we have 8 times 3 plus x over x squared plus 3 plus x squared, and that'll give us our length squared. Okay, so why do we do this? A good way to think about this is we're trying to get two variables in terms of one variable so that we can optimize that one figure of your function or your image or your argument or whatever you want to think of it as. All right, so let's go ahead and expand. Let's multiply that 8 and expand and simplify our entire function. For the sake of not making this video too long, once we expand and combine like terms, well, don't expand your 3x, you can factor that out. You're left with x plus 3 squared times 1 plus 64 over x squared. All right, now let's go ahead and find our derivative. And yes, for your derivative, you have to use product rule. There's no way around it. All right, so product rule, let's find the derivative of our first, and we have to use chain rule. So I have 2 times our inside, and then the derivative of our inside is just 1. So we can choose to not write 1. Times our second, so 1 plus 64 over x squared, plus our first, times the derivative of our second, and for the sake of not going into quotient rule, let's think of this as 64x to the negative 2. So once I take the derivative of that, we get negative 128x to the third, divided by x to the third power. All right, let's clean that up and get that under a same denominator so that we have 2 times x plus 3 times, well, yeah, x cubed minus 192 all over x to the third power. So all I did to get from here to here is get the same denominator. Okay, so now that we have our derivative, let's go ahead and set it equal to 0. If we set it equal to 0, that just leaves our numerator. Because we multiply denominator both sides, it can be multiplied by 0 and it'll be gone. I can't write 3s for some reason. Okay, so let's go ahead and solve our numerator. And we're left with x plus 3 equals 0 and x cubed minus 192 equals 0. I solve for x, I get negative 3, which is not a good value because our x is going to be a length. I can't have a negative length. That's not a good one. And then once I solve for this one, I can use the square root or the cube root property. It gives me x is equal to the cube root of 192. And that, if we punch that into a calculator, it's about 5.77. Let me double check. The cube root of, yeah. So that is our value for x. Now with that, I can go ahead and finish our problem to find that length for our ladder. All right, I'll let you finish that one off. So this is pretty much optimization problems. So in summary, you're trying to work with 2 equations at a time and kind of work with them so you can get everything that was in 2 variables into 1 variable, just as we did in this first problem. And once you do that, you're able to set your use your derivative, find your derivative, set it equal to 0 to find a potential maximum or minimum. It depends if it's asking you to maximize or maybe if it's a price, you're trying to find a minimum for some value. All right, that's section 4.5, optimization problems. Thank you.